All right, Chris, what's up?
75, 384, or 385.
3-5 number.
75.
Oh yeah. Okay. So today we're going to actually get into graphing trig functions. I don't know from your perspective what this is like, but we haven't graphed any trig functions yet. We have a unit circle that's just a circle in its own. And right now, how do the trig functions relate to that unit circle?
The ratio.
Yeah, so if I draw triangles within it, they're ratios to the sides of the triangle, or just from the unit circle itself, they're just x and y pieces and ratios of those pieces. Are you guys with me? So the unit circle in a way contains all 6 trig functions at once, right, in itself. We haven't graphed any single trig function yet. We haven't made an xy table for sine and then graphed it. There's a lot of little areas in this book that I disagree with when they bring in certain ideas, and this is one of them. So they bring in the idea of even and odd. And now if you guys remember how to test for even and odd symmetry. So if you take f of negative x, if that's equal to f of x, it's even.
Yeah.
So think about x squared, even power, right? This is one reason why it's good. It's a way to remember even symmetry. 2 squared is 4, negative 2 squared is 4. When I plug a negative value in, I get the same thing as positive value, even symmetry. So if f of negative x equals negative f of x, odd symmetry. Now, the reason this is evil to put this in here is it's just symmetric. What is even symmetric with? What's the mirror for even symmetry? The y-axis is the mirror. And we haven't graphed the damn trig functions yet, so we don't have a good visual of why it makes sense. They just gave us the properties. So I'm going to revisit this later once we got some of these graphs down. But for right now, they give you this whole little chart to tell you that sine of negative t. In fact, let's try this out. What's sine of pi over 6?
The sine is 3. It's 1/2. It's 1/2.
It's 1/2. Good, right? It's close to the x-axis. Sine should be smaller because sine likes y. If it's close to the x-axis, sine's like, oh shit, right? Little turtle dude, you pull it back in. He's only 1/2. Yeah, what the hell? I don't know. Whatever gets in your head. I liked it. What's sine of negative pi over 6? How does that relate? It's going to still be the same value. What sign is it going to have? S-I-G-N. Yeah, it's going to be negative because sine, of course, in the 4th quadrant is negative. So when I put a negative value in, it's a negative what it used to be. So which one is sine?
Odd.
Odd. Sine is odd symmetry because when I plug a negative value in, I get the opposite of what I got out before, right? So they tell you that sine of negative t is negative sine of t. Cosine's even. Right? You can do the same thing. If cosine of pi over 6, cosine of negative pi over 6. Why are they the same value? Cosine likes x, and what's the x-axis in the 1st and 4th quadrant? The x values are positive. So cosine is going to be even. So they tell you cosine of negative t equals cosine t. And then they give you the rest for the other 4 stuff. So that's on page 382.
So how do you determine this one?
So in general, I don't care what function I give you, how do you figure out if it's even or odd symmetry?
Plug in a negative x.
Plug in a negative x and see what the hell happens. I don't care what the function is. That's the test. Now there are other symmetries, but if these are the only 2 I got to test for, that's the only test I got to worry about. So they give me a function, what's the first one there? Well, we'll do this one, just to do it different. So how do I test this for symmetry?
Plug in a negative x.
Plug in a negative x. I'm going to plug a negative x in. Obviously, negative x squared.
Positive.
Yeah. So all I got to worry about is cosine. What does cosine do to negative inputs?
Keep them positive.
It makes it the same as it was before, right? So negative x squared is still just x squared. Cosine of negative something is cosine of that thing. So is this the exact same as it used to be?
Yes.
Yes, therefore it is
Even.
even.
How? How is it still even with the cosine portion?
Because what is cosine itself? What is cosine itself?
Yeah.
Cosine is even. So in a way it makes sense. You have an even function times an even function. That's going to come out even. So on one level, I don't like that they introduced it this early because we don't have a visual in our head. I know a parabola is even because I can see it. And there's a y-axis running right down the center. I can see it. Can you guys see the sine and cosine? You sort of can, but you don't know the specifics. You know it's like, is that? But that's not good enough to know if it's even or odd. Right? I don't blame you. I haven't talked about it yet. So I disagree with them giving us this early. But on the other hand, this is all you got to do to test for symmetry. And when you plug that in, you just reference that chart they give you, that little box, and say, okay, cosine of negative something is cosine of positive thing. It stays the same. And you know the test for even and odd is just plug in a negative x and see what the outcome is. Is it the opposite of what it was? No. Is it the same? In this case, yes. So what about this one? So how would you test that?
Plug in a negative x.
Plug in a negative x.
It's even. I mean odd.
Yeah, what does sine do to negative? I know the first part's going to just be x squared. That's even. What does sine do to negative input? What's a negative input do to sine? We say it that way.
Keeps it negative.
It makes it the negative of what it used to be. So this will be times negative sine 2x. So this is the exact opposite of what it used to be, right?
Yep.
Therefore, this function must be odd. Because if you plug it in, it's the opposite of what it used to be. It's odd. So on that level, it's just plug in a negative x and just look at what happens. And if you got to look up what tangent or cosine or sine does, they give you the little chart to look it up. I don't like that though. When we get into graphing them, I'm going to revisit this and show you why it's even, why it's odd. It's a lot easier when we can see the damn things. We don't see them yet. Yeah.
So how come you put the negative ones in all the way on the outside
Say again?
of the x squared? How come you put the negative there instead
Because it's,
of x squared?
well, alright. So if you want to, so this will be x squared times negative sine 2x,
Okay.
which is negative x squared sine 2x. Yeah. All it matters is one part of it became negative, so the whole part's negative. Now here, I'm going to throw this at you. I can see you guys are all a little less receptive right now, well, even and odd, but I don't care. I'm going to throw this at you anyway, so if you pick it up, awesome. I always think about, now you notice when it's even times even, it stayed even. When it was even times odd, it became odd, right? So it's kind of neat. Even I can think of as a positive, and odd I can think of as a negative. So if I have even times even, that's even. Because odd times, positive times positive is positive, right? What's odd times odd? Even. Because negative times negative is positive. And what's odd times even, or even times odd? Odd, because negative times positive is negative. And real quick. X squared, is it odd or even? Even. If I multiply that even times this odd, I of course end up with a odd, right? That's all we're doing. Remember, that's the basic reason why we call them even and odd, because they relate to these basic polynomials, x squared, x cubed, x to the fourth, perfectly. If it's an odd power, it's an odd function. That kicks so much ass. You don't even know, right? And so of course if I do even times odd, it's going to come out odd. Right? That's exactly what we had here. Even times odd came out odd. Just that when we have functions that aren't powers, we lose that nice easiness, but all the same rules apply. Okay, hopeful. All right. Shake that one off. Okay, so anything else from homework?
No.
Yes?
I have a question about that. The cosine negative t equals cosine t. Is that a property or rule from one of the sections?
Yes, this one.
Okay.
Yes.
5%.
Page 382 lists those even odd properties. And again, personally, they came in too early. They should have waited until the next section. Because even an odd is a complete visual idea. So why bring it in until you have the visuals? So the next section will have the visuals. Okay. Cool. Maybe. Some of you guys are with me. All right. Is there anything else from homework? Okay, all right. Let's finish up that thing from last time, that handout. And don't forget, tomorrow we're having a quiz. Basically, it's on the exact same sections.
Do they get it going to look like this?
Well, yeah, pretty much. Oh, cool. Got it free. Alright, so where we leave off? We left off down here. Number 6. If you want a copy of this, I can give it to you after class. Alright, so we finished off number 4. We figured all the sides and all the angles. So this one, the easy first thing you get is how big is this angle here going to be? Yeah, y is going to be 25. Yeah, the other two have to make 90, so overall you get 180. Cool. So let that part be easy. Now, what side could I figure out? What side do I know? I know hypotenuse. So I definitely can't use tangent right now, right? Because I don't have either of the one sides. I could use sine or cosine. Or if you really feel like cosecant and secant, let's just stick with sine and cosine. If I want to do sine, I would do sine of 25 because 25 degrees is in the base. But if you do it the x, y way, you have to do it with the angle in the base. The only advantage SOHCAHTOA has. What would sine of 25 be? Let me label my stuff here. What's the sine of 25 degrees? Y over 40. Yeah, y over 40, or whatever you call that side. Whatever you want to call it, doesn't matter. Y over 40. Let me just stop right there. Is that by itself understood? Is that cool? That is so huge to just understand what we just did, because that's really the power of trig. I can use my calculator to figure out what sine of 25 is, and it's equal to any ratio of a right triangle with that angle in it. Right, the right ratio, the y to 40, the y to the hypotenuse. Right? So whatever triangle I'm working with, that sine 25 is powerful. It's not a value you should know. You're not memorizing sine of 25, but it's a value my calculator can just spit out at me. And we're actually going to talk a little tiny bit today about how the calculator does it. It doesn't have a table of values it looks up, right? Now, solving for y, how do you do that?
24, 3 times 40.
Yeah, 40 times sine 25. So making sure your calculator's in degree mode, right?
16.9.
16.9 roughly. Yeah, double check that, cool. And again, if you're going into physics, even if you're not going into physics, I don't care. The sine is kind of cool. The sine is sort of like a percentage of the hypotenuse that's in the y direction. And the cosine is sort of a percentage of the hypotenuse that's in the x direction. It's not exactly percentage because it's squares. It's not linear. But I don't care. It works beautifully like that. Especially taking anybody ever had any physics at all? And you have problems like somebody's pulling on a crate and the angle that I don't know if you guys did physics at that level. But you have to use trig to figure out, well, how much I'm pulling on the crate at an angle. Well, how much is that pulling? How much is it pulling it up? And how much is it pulling it over? So if I increase the angle up, then I'm going to decrease the friction on the thing. If I pull it off the floor a little bit, the friction is going to be less. But also I'm going to have less actually going in the direction I want to go. So it kind of sucks. So somewhere there's an optimal angle to pull this thing at. It looks like I'm making butter or something. But I can pull this thing so that I pull a little bit of friction away, but I'm still pulling it in the way I want to go enough to go there. Anyway, that's a little bit beyond, but still, it's kind of cool. The idea of that. So what percentage of the hypotenuse is in the x direction I use what trig function?
Cosine.
Cosine. Right. Or I could just do,
The tan.
I could use tangent, or I could use Pythagorean theorem. Right. But again, personally, I just always wanted to start with stuff I know for sure. So I would do cosine of 25 is what? How do I make it?
X over 4.
X over 40.
Beautiful. The x side over the hypotenuse. X over 40. So x is 40 times cosine.
Cosine.
36.25.
Yeah.
36.25?
Yeah.
Oops, there it is. Why does that make sense? If it's only going 25 degrees, which one should be bigger, the y or the x?
Yeah.
The x should be bigger. That's what we just got. Makes sense.
So why should the x be bigger? Because we're going 25 degrees, because that's the base.
Because if I'm at 0 degrees, let's say I'm 40 here, and I'm at 0 degrees, then I'm 40, right? If I take this sucker, if I take 40 and take it up 25 degrees, most of it should still be the x.
Oh, okay, gotcha.
Because I haven't gotten to 45, which would be exactly where they're equal. And if I go to freaking 90, then it's all y. That's why cosine is biggest at 0 degrees and sine is biggest at 90 degrees. Cool.
Gotcha.
Okay, good, good, good. Like it. Most of you guys are not like it, but that's all right. Does it make sense? Yes, sir.
So the for the x, you put like the unit symbol of the degree on 36.25, but not for the y.
Oh, not degrees, sir. I don't know why, but it's not
So
degrees.
wait, where did the degrees come
It's not degrees.
Okay.
My bad. So whatever units I give here, feet or meters, I didn't really give any, so this is just the length. Yeah. So this guy, what's this last angle here?
54.6.
54.6, good to make 90 between those two. If I just do this little bit here, how do I find? So I've got the y piece, right?
Use tangent.
Yeah, I can use tangent to get the x piece.
Yeah.
What do you call it? H for hypotenuse.
Tangent of 35.4.
So tangent of 35.4,
53 over.
good, is equal to y over x. I really, oh. So once I pick the angle, any trig function I choose to use on it, if I chose to use sine here, sine of this angle would be y over hypotenuse. So I can set up the ratio, and then I fill in what I know, and I solve for what I don't know. So we use tangent. Tangent of this angle would be y over x. I know y, I don't know x, now I can solve for x. And this illustrates the basic idea of trig functions. They're just ratios of sides of triangles. That's all they are. And you can do so freaking much with them. So this is the most basic thing you can do with them, is use their definition. They're defined to be ratios of sides of triangles. So what do you get here? So x would be 53 over
74.5.
so this is a sigma transition. So who is it, sorry?
74.59.
74.59. And that kind of makes sense. Obviously, got to be the biggest side.
Yeah.
And then how to find what is the x piece? I mean the hypotenuse.
Pythagorean theorem, or you did.
Yeah, either Pythagorean theorem or what trig function can I use?
Sine.
Sine. So sine of 35.4 would equal what?
92.49.
53 over h, right?
Yeah.
The y piece over the hypotenuse. If you solve for h,
53 over 7.
Yes.
91.49.
91.49. Now, why does it make sense? So let's take a step back here. That makes sense at one level because the hypotenuse is the largest side. X has definitely got to be bigger than y because x's angle is bigger than y's angle. You guys with me? This opens up only that much, so the side across from it can't be as big as the other side. Does that make sense in itself? This angle only opens up 35.4 degrees. The other angle opens up 54.6 degrees. It can fit a bigger side in its mouth, right? Here's his alligator. And it can fit that big of a side. That dude's freaking opening up wide. so it can fit a much longer side in its mount. I'm thinking about the Rancor from Star Wars, to be honest. Just to be a complete and utter geek. Alright. Well, whatever the hell you want to think about. How are we doing so far with this? Don't let this be difficult. If you know your ratios for sine, cosine, tangent, so forth, right? And if you know those three, you know all six, because the other three are just reciprocals of those, right? If you know them, you could set up any equation you need. You just need how much information?
One angle.
I need one angle
And a side.
and one side. If I have one angle on one side and a right triangle, so I actually have two, but if I have one angle on one side beyond the 90, I can get everything. That's pretty damn powerful. You can never do that before. Alright, so let's talk about Mount Doom, just continuing the theme of being a complete geek. So we are hobbits. We are. You didn't know that. We are hobbits walking along towards Mount Doom. At one point, we measured the angle of elevation, so we're walking towards the mountain here, right? Right here, we measure the angle, and we see it's 32 degrees, right? Then we go 1,000 feet more, and we measure the angle again, and it's a little bit bigger. Now, of course, why does that make sense? The closer I get to the damn thing, what happens? I can see the top if I just look there. If I get closer, now I've got to look there to see the top. That just makes physical sense, right?
Yes.
Very good. So thank God that makes physical sense. Now, when you're first looking at this, I don't know how you think about it. When you look at a problem like this, we have to find what kind of shape?
Right.
Right triangle, exactly. Not just a triangle, a right triangle. Later, we're going to learn something called log sines, log cosines, and we can do any damn triangle we want, or that you're given. You might not want to do it, but well. So I've got a right triangle here, and I got this big ass right triangle there, right? And I know base angles for both, which is good. So for the big ass triangle, what could I set up? What's true about the big ass triangle? What relates what I know to what I want to know?
Tangent of 32.
Yeah, so the tangent of the 32 that's in the big one,
Because h over
it's got to equal the height.
over 1,000.
And what's this total side here?
X plus 1,000.
Yeah, I call this x2 because I think this used to be x1. I had it differently set up, so don't worry about that 2 there, really. It's not squared, at least, right? It's just x2. You guys know it's not squared when it's down here.
Yeah.
So please don't anybody tell me that you square rooted somewhere at the end. Alright, that's one thing. Now, what sucks about trying to solve that?
You get two variables.
Get two variables. So, of course, I need one more piece of information. It's going to be a system of equations, really. Right? So, what can I do about 35 degrees?
Tangent
Make it into another equation.
h over
It's crazy. Yeah, this will just be, for the littler triangle, it's just going to be h over x. Now, which letter do you not care? Which one do you need to solve? So, which one?
You need to solve for each.
Need h, don't care about x.
Right.
Right? I highly recommend you solve each of these a little bit. At least multiply this up. Now, this one you can solve for x all the way. But you don't want to solve for x and throw it in here and then you have fractions inside fractions. It just looks horrible, right? Let me give myself a little more room here. So if I solve this one for x,
Yeah, should be.
I get x equals h over tangent 35. If I multiply this bottom up on this one here, I'll get h equals tangent 32 times 1,000 plus x. How we doing? Yeah, I could distribute, do all kinds of stuff. I could throw this guy in here, right? But it's just a system of equations. I know it's got tangents in it, but what is this? What is that? Don't try to tell me the answer, because 35 degrees is not something we know. Well, what is tangent 35 degrees? What is it? Physically. So it's a ratio which comes out to be a number. I love it. It's just a number. It's like ln of 14.8. You just bring it with you. You don't care what the hell it is yet. But it makes it more easier to carry it around with you, right? Okay, so what's this going to look like here? So if I have h equals tangent 32 times 1,000 plus, and here's what x is.
That's the.
And now you gotta solve for H. So of course, what do you always do when it looks like you have more than one variable? Eventually you want to get
H is on the same side.
all your H's on one side, because then you can pull them out and see that there's really only one of them. So you get 1,000 tangent 32 plus H times tangent 32 over tangent 35. Is that cool? Just multiply that in. I just want to write this a little more like an H out here by itself. So to solve for H, I just have to... What's the next step to solve for H?
I'd say subtract H.
Yeah, get all my H stuff together, because then I can GCF that bad boy out. Right? So I get H minus H tangent 32 over tangent 35 equals 1,000 tangent 32. I can factor an H out, divide by the mess I don't want. I desperately want you guys to see that this is sort of like dealing with natural logs, trying to solve those really ugly natural log equations. The 3 to the x plus 1 equals 11 to the 4x minus 7. We had to keep track of all this stuff, right? Same exact idea, really. So let's see, third piece of paper here. So now if I pull an H out, I get H times 1 minus tangent 32 over tangent 35 equals this business. So I just got to divide by that thing to get what H is.
It just seems a whole lot messier
Yeah.
Messier than...
than how I did it.
Oh, okay.
Like I solved for H here, so tangent 35 equals H, and then I same thing here. So H equals all of this, and I just input those together.
Wait a minute.
So you get 1,032, or tangent 32 plus that, and then input this here, and then basically I just did the same thing. Where I
This is
solved.
H, this equals... Oh yeah, okay. Alright. Cool. So, I have this weird feeling that nobody's trying to do this. It's probably unfortunately true. Anybody trying to do this?
Do what?
It's definitely, to tell me what the hell it is.
Oh, it's 5,807 point blah, blah, blah.
5,807.6.
Uh-huh. 6 feet.
6 with some shit after it.
Okay. No C shit. Cool. Okay. Which is roughly the only references I could find in how solid anything is. Roughly that. So, I mean, that was obviously, now, from number 4 to number 5, that represents a huge step, obviously, right? But they both depended on just setting up the right ratios, using the right trig functions that related what you know to what you want to know. Number 5, I just had too many unknowns. That's why it's worse. I needed 2 relationships. But how did I set them up? I used tangent because tangent related what I want to know with what I know. So just remember, that's the basic of any of these trig problems. The flagpole problem we did before, so forth. I mean, those kind of problems they're going to deal with. Which trig function do you want to use that relates what you need to know with what you currently know? Okay. So that kind of problem, I think they start off in 6.2, definitely had something like that. So we have like the parallax problem. I mean, the star you can see. Yeah.
That's like the flag, isn't it?
And the flagpole problem we did. Okay. So there's no other questions on anything we've done already. We're going to go and get into section
5.3.
5.3.
5.3 and
Yeah.
6.3.
And I tell you, you'll see very quickly, you all know what sine and cosine look like. Right? They look like that. Would sine and cosine, the way they are, would they have inverses?
Sure.
Yeah. No.
Why would they not?
Because they don't.
What test are they supposed to pass to have an inverse?
Oh, they're going to pass the horizontal inverse.
Horizontal. Vertical just tells you it's a function. So they're functions. I already told you that. It's got to pass a horizontal line test to have inverses, right? So we need to first talk about the graphs of them before we can talk about how to adjust them so that they will have inverses. Section 6.4 is all about trig inverses. Well, wait, what the hell? We just said they can't have a freaking inverse. Yes, they can if we restrict the domain correctly, right? Remember, parabola can have an inverse if I cut out its negative half. You got it with me? So that's why I have to do 5.3 before we can do 6.4.
6-3. Or are we doing
6.4.
Did we do 6-3
We
already?
already did 6.3.
I don't remember.
Okay. So, first thing first, whenever you get a new, let's just say X, a new function to try to graph, you need to get an X1 table. So let me give you the values to plug in. That's as many as you should have to do, right? Because then after that, what happens to the values? What would happen? The next thing I could do would be 2 pi over 3. And what would happen at 2 pi over 3? It'd be the same as pi over 3, and it actually it'd be positive. So that sine is going to build from, what is it at 0? Sine of 0 is sine of 0.
0, 1.
0, because sine likes y. How much y is there if you're on the x-axis?
0.
None. So at 0 degrees, it's all x. That's why cosine of 0 is 1. Gotcha. That's really what you guys were. So sine of 0, 0 is going to build up to, of course, 1 here. And then it's going to start to decrease again. And you know this. Where does sine become negative for the first time? Which quadrant? Third quadrant, because that's where, what's sine based on, x or y? Y. So where's the y values actually become negative? Yeah, the third and then the fourth, yeah. So the first time sine's going to become negative is after you plug in pi. So you're going to get all the same damn values, all the same outputs are going to come out. You just have to be careful about the SIGN, sine, is it positive or negative? Right? You have to start spelling out sine when you start talking about trig. So I want you guys at least finish this out, plot that much, try to figure out how it's going to go past there. These are all the values you should need. It's going to grow, shrink, grow negative, shrink negative, but it's going to be the exact same value. So try to finish this out and try to even start plotting. Go this far maybe at least. Finish the table values out. You should know these.
Are we talking about right now?
What's that?
Are we talking about these?
Yeah. Yeah, you know what sine of pi over 6 is. You're supposed to.
Right.
Yeah. That's all I'm saying. Just finish that table out.
Yeah, but isn't the x of pi over 6 right here over 2?
What do you mean? What's the matter? Cosine pi over 6 would be that. Sure.
Right.
Yeah. Of course, when you get rad 3 over 2, you can make it a decimal approximation whenever you have to graph something by hand. So one time, I don't have to see rad 3 over 2 from you. I can see what the decimal is. So what's sine of pi over 6?
1/2.
1/2. Sine of pi over 4.
That's right, 2/2.
Which is 0.7, blah, 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 blah. Right?
Right there.
Cool. That's good enough for by hand. We're at 3/2, which is
0.9.
point.
8 or 9. 0.866.
0.86.
Yeah, let's make it 0.9. And we're doing it by hand, so that's 1 decimal place. It's really more than I can capture with my hand, that's for damn sure. Right? And what's it going to do back here then?
Go back.
Go back.
Go back down. 0.9, 0.7, 0.5, so forth. Right? Okay. So here's pi over 3 roughly. I'm sorry, pi over 6, pi over 3, 2 pi over 3, so forth. What's up? So at, so let's see. The most it's going to be is 1, and the least it's going to be is -1. So at 0, it's 0. At pi over 2, what did I just do here? Why is that wow? Pretty freaky. My bad, my bad.
It's graphing.
Thinking further down the road. At pi over 2, it's going to be 1, right? And at pi, it's going to be 0. So these other points in between just sort of give us a feel for, is it like a triangle? Does it curve down? What the hell does it do? So at pi over 4, we got 0.7. Let's see. 1, 2, 3, 4. No. Half. Quarter. All right, so 0.7 is roughly here. At pi over 6, we got 0.5. So you can see it's got a building. Oops. Building up like that. And it's going to go through the same points down this way. So it's going to come back down like that, that big. And what's it going to do past pi? What did we say earlier? Once it gets to pi, it's now in the 3rd quadrant, so now it's going to be the exact same shape, just negative values. Cool. So that's basically going to go that down to 1. So at 3 pi over 2, it's going to be -1. That goes back here. And it keeps doing that forever. Now, a real quick visual of this. Real quick little get what's going on here. It's kind of nice.
So you'd have it restricted to power 2.
Well, we'd have to look at the negative stuff too. So what's it doing back here? Same shape, just negative. So if I restricted it from negative pi over 2 to pi over 2, would that piece be invertible?
Yeah.
Yes, cool. So then we can figure out what sine inverse would be. The outputs for sine inverse would only come up between -90 and 90 degrees. Now, this is kind of cool. Well, let's see. Is that the one I want to show you first? Yes. It's the only one I got up there. The top one is, of course, the important one. The other two are just kind of neat little, what would happen if it was a unit square, right? So the circle, it's picking out the y values as you move around the unit circle. You with me? So as I move around the unit circle, I'm going through a certain angle. And when I go to this kind of picture, I'm putting the angles on a straight line instead of in a circle. So as this thing moves, it's also moving the tape of the xy plane here, right? So at 0, it's 0, and then it kind of spells out that shape we got there. Cool. I love that visual. Back in my day, we didn't have these kind of things. Just had the teacher trying to draw. He was worse than me. Imagine that. And he ate chalk. It's a little scary. Okay. That's sine. What would cosine look like?
It would start at 1.
Yeah, it starts at 1. So it's like, how do you think cosine... And then, of course, it has all the same exact values as sine, just offset. By how many degrees? By 90 degrees, right? Every 90 degrees, they switch values. So at 0 degrees, cosine is 1, sine is 0. 90 degrees later, sine is 1, cosine 0, right? So forth. So they are. So if I started at 1, if I pull this back here, and when. That would be what cosine looks like. And to be very specific, where do they tell you this? Say again?
Why does it start at 1?
Because what's cosine is 0. Okay. I don't know. Did they tell you this eventually? No. Those dorks. Too bad for them. They do tell you this. This is something you should have picked up on before. If I take any value and I go, let's just do this one. And I go 2 pi later. So if I'm on a unit circle and I go around 2 pi, where do I end up? Same point. So that would mean they do have this little dude. Sine of x plus 2 pi is sine x. Because you end up right back on top of yourself, right? Not a big deal. That's the periodicity of this thing. So we say that the period of sine and cosine is 2 pi. Because that's how long it takes to go through all the possible outputs. So all the possible outputs would start at 0, get all the positive ones, all the negative ones. So it takes a full 2 pi to go through all that.
Just like the gift.
I love it. Exactly. So the period here for sine and cosine is 2 pi. Now, since we have this picture up here, and I really didn't give myself enough room, that's too bad for all of us, really. But what's related to sine? Which one of the other 3? You got sine, cosine, tangent. Cosecant. So cosecant is 1 over sine. So wherever sine is 1, cosecant is 1, right? Because it's 1 over 1. Wherever sine, you guys, so cosecant is how related to sine? 1 over sine. So if sine of x is 1, cosecant of x is 1. If sine of x is 0, cosecant x goes to infinity, plus or minus. Right? Undefined. Another way to say undefined is it's infinite. Right? Well, we know better now. It's actually infinity or negative infinity. That's really what undefined is trying to say. There's nothing defined because you can't get there because you're going to infinity right next to it. So what would that look like? Where would there be asymptotes? You know exactly where they would be up here. Where would there be asymptotes? Wherever sine is 0. So where's sine 0? A pi, so there'd be an asymptote here. So in green it's going to be cosecant.
And that's 0.
At 0 there's going to be
A 2 pi.
and then back here, a negative pi, and a 2 pi.
So every pi.
Beautiful. All the multiples of pi, there's going to be asymptotes for cosecant. Just because cosecant is 1 over sine. So of course, wherever sine goes to 0, cosecant's undefined, which means infinite, an asymptote. So it starts at 1, and as these values go down, 1 over them is going to go
Down faster.
If I make these smaller, this is like, what was pi over 6 is 1/2. Right? So pi over 6 is 1/2. So what is 1 over 1/2? 2. Right? So I'm going to be at 2 there. And the same thing over here. So it's kind of cool. They're just these parabolic looking dudes sitting on the top and bottom of the sine. Because over here it's going to be negative outputs, right? -1. So what's cosecant? 1 over -1 is -1. And then it's going to approach the asymptotes. Well, that's really extreme. Too bad. Whoa, that looks disgusting. It's like it looks more parabolic. Right? They have a really nice picture of it. Much better than I could do. Actually, to be, I didn't really want to let this out, but it's too bad. We are sort of looking at that section 5.4 right now a little bit.
So would this be the same thing also with the not the cosecant, but the other one,
Exactly. So if I had a picture of cosine,
yeah, I think.
its reciprocal is secant, the exact same idea, except it would just be shifted back by 90 degrees. Right? So since cosine would start here, its secant would be here. Do you guys see that? Do you understand what I'm saying? It's just a direct consequence that, in this case, cosecant is 1 over sine. So this must be what it is. Once I know what sine looks like, I know what cosecant looks like. It's 1 over all the freaking values we just did. So all these are fractions, so 1 over them are going to be bigger. It's going to go to infinity on either side. So cosecant is definitely a funky function. Just because sine goes through 0 infinitely many times, cosecant's going to freak out that many times. Yeah, maybe. So this would be the exact same setup for cosine and secant if I just move the axis there by 90 degrees. It'd be the exact same picture for those. So visually, it's kind of nice that these trig functions are not too far off from each other, right? Visually, they have the same shape. They're just offset, in this case, by 90 degrees. So what the hell would tangent look like? Let's see.
Keep your camera a little bit.
Oh yeah, thank you. It's great. It's all good. I appreciate it. Anybody, anytime, anybody, tell me. I am very focused on one thing. I forget other things. Let's just look at some really major values here. 0, pi over 4, pi over 2. Let's get a feel for what's going on. Tangent's kind of nice. It's very, because that's what I want. What's tangent of 0? 0, because it's sine over cosine. Sine is 0, cosine's 1, so it's 0. Of course, tangent pi over 4 is 1, because that's where sine and cosine are equal. And tangent is just sine divided by cosine. So anywhere they're equal, it's going to come out 1 or negative 1. And of course, what's tangent of pi over 2? Beautiful. So there's going to be an asymptote at pi over 2. And probably, if I go the other way, it's going to go the other way. Negative pi over 4, negative pi over 2. What's tangent of negative pi over 4? Which quadrant are you in? Fourth quadrant. Sine and cosine have different signs, so the tangent's going to be negative 1. Good. And of course, tangent of negative pi over 2 also has to be undefined. Now I can fill in, like Chris wanted, and I don't blame you, you can look at pi over 6, pi over 3, and they can kind of fill in the middle parts. But we'll get the shape from this well enough. So if I go from negative pi over 2 to pi over 2, so those are the places we found there's asymptotes. At 0, it's 0. At pi over 4 and negative pi over 4, it's 1 and negative 1 respectively. And what's it got to do with these asymptotes? It's going to run up against them, right? So it almost looks cubish. Yeah. It looks really close to cubish. So it come in, make that big. And I want you to really realize this. It does this how many times? Infinitely many. So from pi over 2 to pi, pi over 2 to 3 pi over 2, it's going to do the same thing again, right? It's going to have asymptotes.
It's going to go the opposite way.
No. And think about it. Once you're in, how do I say this? Which quadrant am I in here?
Third.
Second quadrant, right? 90, and in that quadrant, there are different signs, aren't they? So it's going to go negative. So tangent goes positive, negative, right? So positive, negative. So it's going to repeat that same shape forever. Now, can somebody figure out for me what the period of tangent is? Period of sine was 2 pi because it's how long it took it to go through all of its possible values. It's going to continue this shape forever, right?
So it'd just be 2 pi over 2.
Okay, sure. Which is pi. From negative pi over 2 to pi over 2. It's pi across. So the period for tangent is pi.
I don't understand what period is.
A period is how long it takes for the function to tell you all of the values it could possibly have. So if I only go from 0 to pi for sine, it's only told me the positive values. It's got to go from 0 to 2 pi And in fact, a little more technical definition, it's got to be doing the exact same thing, and that's when you stop. So here's the same value, but is it doing the same thing?
No.
No, it's going this way, right? So I got to be going this way. So what's the next time? It's going that way through 0. There. So from 0 to 2 pi. So here, asymptote. The next time it's got an asymptote is there. Right?
Since it's doing the exact same thing, that's why it's only 1 there. What about then with the cosecants?
Yeah, what about secant and cosecant? What do you think? Considering they're just reciprocal functions, they still are 2 pi. Here it gets all of its positive in pi, all of its negative in the next pi, so it's got a period of 2 pi cosecant, right? Cosecant's got a period of 2 pi the same way. It takes that long for it to tell you all of its values.
How do you graph these secant x?
Oh, so like I said earlier, if I move this y-axis here, then I have the cosine and I have the secant. So this is the shape of the cosine and secant. It's just that it's offset by 90 degrees. Is that cool? So just a quick way, instead of recreating it, I just say, well, imagine your y-axis is here. There's your secant. There's your cosine. Yeah.
So for sine, you're always going to have 2 inverses? Or
Reciprocal functions. There's only one reciprocal function for sine, and that's cosecant. But if I did move this over, now I'd have cosine and secant.
Okay.
You guys kind of, if I move this here, 0, pi over 2, so forth, that would be cosine, and this would be secant. Yes?
Would cosine be like a negative x cubed function?
No. There's so many things that look, in fact, we've seen a lot of them when we had to do all the graphing stuff. Every one of these looks parabolic. They all look parabolic. None of them are true parabolas. They're not truly symmetric in the right way. They don't have the right curvature. So that looks cubish. It's not. You can't approximate it directly with just a cube function. Otherwise, why would we have tangent? We just say, let's use the cube function instead. It looks cubish. It's kind of nice, and it makes it easy to remember. So how far off do you think cotangent is from tangent? Where's cotangent's asymptotes going to happen? No? Tangent is sine over cosine.
So it's just going to
So, real quick, hold on. Tangent's asymptotes happen where what?
Where cosine,
Cosine is
Where
0.
cosine is 0.
So that's 0.
So that would be, for cosine, it would be negative pi over 2 pi over, any multiple, any odd multiple of pi over 2, it would be negative pi over 2 pi over 2, 3 pi over 2.
Sine over sine.
So cotangent is cosine over sine. So it's going to have asymptotes where sine is 0. Sine is 0 at 0, pi, all the multiples of pi. So again, same exact shape, but how far off are they then? If this is at pi over 2 and cotangent starts at pi, they're still 90 degrees off. Right, exactly. Kind of makes sense because they're built on functions that are 90 degrees off from each other. So cotangent theta is cosine over sine. So it's going to have asymptotes when sine is 0. So to give you that, it's the same exact picture. It's just all the asymptotes in the picture shifted over by 90 degrees. That's all. It's the exact same picture, except for one thing. So let's do this one. It does have one difference. And this is sort of like what somebody asked earlier. It was here. If it was going to have the same shape. So real quick, for cotangent, so now we know it's going to be 0 to pi, for example. So cotangent of 0 is infinity. What's cotangent of pi over 4? 1. That's where they're both positive, right? So this is still going to be 1. That's where they're both equal to each other. So it's going to be 1 here. Cotangent of pi over 2?
0.
Good. Cosine is 0. Sine is 1. What's cotangent of 3 pi over 4? Now what quadrant am I in at 3 pi over 4?
two.
Second quadrant, sine and cosine have what kind of signs?
Negative.
They're different signs, right? Cosine is negative, sine's positive. So the cotangent's going to be
Negative.
-1. So now instead of looking like that, they have the same shape. It's just
Backwards.
flipped. Exactly. So it's going to look like,
Well, that's what I was asking.
yeah, that's cotangent. Tangent maintains that same shape. Cotangent flips that thing, right? And it's going to keep doing this forever in both directions.
And it's still pi.
Yeah, exactly. Still has a period of pi, which makes sense because they're just reciprocals of each other. They almost have to have the same period. So the period here again is pi.
Wait, they almost really do.
They do.
Okay.
Yeah.
So I feel like if you say almost, and you're gonna give us the same over.
No. So normally with these things, if you know where things start, you can kind of go from there. And the most important points for sine and cosine would be 0, pi over 4, pi, 3 pi over 4, and 2 pi, right? Those are for cosine and sine. Those are like our anchor points. Sort of like for a parabola, it'd be 0, 1, and -1, right? Those points are for an active value. Because you know what's happening next. I don't know if you realize where I'm bringing, how I'm speaking. Why would I ever want anchor points? Because then I might want to move them around. Exactly. Right. Like I said earlier, that they're off by 90 degrees. That's their period. That's actually could be also their phase shift. How much they've been moved left or right. I can also smush them, which makes a little more sense. They almost look like springs here, a little more closely than any other functions. So you can smush them, make them go crazy, or pull them way out, make them radio waves. Oh yeah. Right. Push them, make them gamma rays out here. Right? Because they have so much energy. So let me give you. Oh, good. What's up?
Oh, I was just curious why you were there.
No, actually,
This here? Alright, so this again is our base points. These are the points I would graph for cosine and sine and then kind of move it from there. Sort of like when I want you to do a translation on a parabola, I would start with 0, 0, 1, 1, -1, 1, and then move those around accordingly, right? You need a few base points so I can move them around. So these would be my base point collection, my inputs. For tangent, it would just be negative pi over 2, negative pi over 4, get in there, 0, pi over 4, pi over 2. That's kind of like the base tangent graph. Because that's like the first place, that's right around the y-axis, that's the one I want to use as the base one, and it just repeats and repeats and repeats forever.
Yes. You could use those also for the cotangent as well.
Exactly. So this is tangent. Well, cotangent, what would I actually use? Cotangent, I would use 0, pi over 4, pi over 2, 3 pi over 4, pi. Just considering that it's offset by 90 degrees, right? It's been moved over. Here's where tangent would sit. This has been moved over by 90 degrees. Of course, this works also for secant and cosecant. Okay. But now, going back to something I said I'd do earlier, and now that we all know what the shape is, we can be a little more loose about it. What's the main thing about a sine graph? What's like one of the most important things to tell somebody? Starts at 0. What? You'd be like in my brain. So the most important thing about sine is it starts at 0. And then I know the basic shape and goes forever. So of course, which kind of symmetry does this thing have? Does it have even symmetry? Hell no, it's not the same on both sides. It's symmetric through the origin. That's odd. See, this is where they should have talked about odd and even symmetry, because now it would be so much easier. What's cosine look like? Cosine starts at 1, and then it goes from there. That's obviously even symmetry. Obviously now, if they would have just put that idea in this section, there would have been no problem. So obviously sine of x and sine of negative x are negatives of each other. Right? If I put an x in, I get there. If I put a negative x in, I'm down there. They're negatives of each other. So that's another reason why it's odd. But it's really hard to just tell you this without giving you the visual of it. The visual is what you need, because that's what symmetry is all about. It's visually symmetric here. So I hate that they gave you this before you had the freaking visual. Okay. So, I'm not going to get terribly deep into this, but I just want to give you an idea of where we're headed next. So, if I start with a base of sine, tell me what each of these would do. Don't overthink it. You don't have to be all technical. So what would happen visually?
It gets taller.
Yeah, it gets taller and deeper, right? So the mountains are higher, the valleys are lower, right? Cool, that's all it does. And this is what's, not surprisingly, we call that the amplitude of it, right? You got your amps, it's the same idea. Turn the amp up, power goes up, the amplitude, the output amplitude goes up. This is the amplitude. So normally the amplitude is 1, so it goes from 1 to negative 1. But here the amplitude would be from negative 5 to an amplitude of 5. You don't say 10, you say from 0, how far does it get away? 5. So that's why I say the amplitude there is 5. Is that cool? So the exact same shape, it would just go up to 5 and negative 5. Alright, good. What would this do here?
Stretch.
Oh, yeah, we
Stretch.
yeah.
If it was a whole number, it would shrink.
If it's inside with the variable, it's the opposite of what it used to. So how did I used to get pi over 2 out? What would I have to put to get pi over 2 out? Pi over 2, right? Not out, but what would I have to put here to get sine of pi over 2?
Pi over
I have to put pi over 2 in. So what do I have to put now to get pi over 2? Pi. So whatever was at pi over 2 is now at pi. It stretches it out, right? Stretches it this way. So it's like taking your spring and stretching it out. So if sine normally looks like this one's going to look like twice. It's going to look stretched out. Still going to be a height of 1 and a depth of negative 1, right? It's just going to be stretched out. How are we doing so far? So nothing changes. Same stuff as before. All the same effects happen. So of course, one of the last things I could do, the last interesting thing I could do, because I can just put a +1, who gives a shit? Just the whole thing moves up 1, right? That's the easy one. -3 just takes the whole thing down. It's the last thing you do. So that's kind of like the least important one. That should be the easiest one. You just do it at the end and just move it that much. But the other ones are freaky. Stretching and pulling and shrinking and shit. Right? That's the hard part. Don't make it I. J of x equals sine. So the only thing left I could do would be something like this here.
It's going to shift it that way. Right.
Shift it to the right by
pi over
pi over 4. Cool. So this is what we call, we're a little more familiar with trig functions. We actually call this a phase shift. Because I don't know if you realize, electricity basically flows in voltage waves, and they're defined by
Phase shift.
trig functions. So you can have two things that are out of phase, and that's not very good most of the time. So you want that you talk about the phase shift. How much shifted are they from each other? All right, so this would be a phase shift to pi over 4 from what's normal. So the terminology changes just a little bit there, but all the effects are exactly the same. So let me give you this one thing, and we'll talk about this next time, but at least I want you to look at this.
So is that everything until we get this?
Yeah, if you get this, you could head on and out. Do you still have that grade sheet somewhere?
Yeah, I had but I have to say,
Alright. Come back to me real quick to the office. Is it alright?
one thing I don't understand on that is where you did the zero.
Which zero?
You know, the X is zero. Where the X is zero part. Most of these, you know how you start with the sign, you put a zero. Where's it on that sheet of paper?
What sheet of paper? Sorry. Which sheet of paper are you talking about?
The one that has all the, you know, all the pies and everything.
Oh, the circle, the unit circle? I think I have that with me, but it's
Is it where it's the 0, 0, 2 pi?
there. That's 0 degrees. That's 0 degrees. No. Careful. Okay. No. This is a unit circle. It's got a function from this. It's not even a function, is it? We are taking the y pieces of all these points and applying them by themselves. And what you need to realize is the x-axis here is not the x-axis here. The x-axis here are the angles. So I took that angle and put it there. That angle, put it there. Right? There you go. So as I move along, what happens to the y pieces? They grow. And that's why as I move along, my outputs get bigger and bigger and bigger, because sine is the y piece.
Where are you getting the 0 on the X?
0 degrees. These are angles. Because what's the input for a sine is an angle. So at 0 degrees, so when the angle is 0, what's the sine of 0? 0. And then I can say, what's the sine of negative pi over 4? It would be back here, right? Negative 0.7. So, yeah, that's all. Good. So as I go this way, it's this way in the x-axis, this way, it's this way in the x-axis.
Now I understand that. The thing I was confusing me is
Yeah, it's the
when
same
you
place
plot
you get
X
pi
and Y,
over
you
2.
put X is 0.
Same place you get pi over 2. It's from that
X is
angle.
not 0. So why is it not doing that?
But this is not a picture of what we're talking about. This is a picture of everything at once, the unit circle. And the x-axis is not even what we want it to be. The x-axis is truly x. I want this to be, I could call it the theta axis to freak people out. And those are really angles now, right? That's what those are. Those are angles.
So I just wanted to make sure if I did this.
Yeah, that's good. Wait a minute, so where is this? Okay, so you did it. Oh. H over X. I don't see how you got from here. Oh, you're solving for X. Okay, sure, but then what we really want is H. You'll get what X is. That's how far we still have to go, but I want to know how tall this thing is.
Okay,
So once you get X, you just use this equation there to solve for H, right?
great.
So, I mean, it's not wrong. You're just solving for that variable. You just got to plug it back in to get the height.
Okay.
No big deal.
I'm assuming the alternate way that the guy who's sitting here uses, he solves both of them for H and set
He just-
equal to each other.
No, he just simplified a little further than we did.
Can't you do that? Can't you take the tangent of the 32 with the H,
Solve for
H
X.
over 1,000?
Solve for X in both, and then set each equal to each other.
Solve
Of course.
for 8, yeah. Do
Yeah.
you want that off?
Yes. Yeah, I guess we don't need all that. You need your